Thank you very much for the organizers to give me the opportunity to be here. So I'm going to talk about work that I've been doing in collaboration with Vlad, or one of our organizers, and Darko Tanaskovic, and a series of students that have worked with us along the years. In particular, I should mention here Tsung-Han Lee, who's here, and Shao Tang, who is also here, but also Marta Suarez-Villagrán and Yaksha Vucicevic, who also gave a poster. We have heard about the Mott transition a lot already, and in particular about this view that of the Mott transition that it should be very similar to the liquid-gas transition. So if you look at the liquid-gas transition, you have this first-order line ending at the second-order point, and you can actually go continuously from the gas to the liquid around that endpoint. And we then look at one of the phase diagrams of these prototypical Mott systems, for instance, V2O3 doped with chromium, you also have this first-order line ending at this second-order point. We heard about this many times during this week. And you can also go continuously around that second-order point, just like you have in the liquid-gas case. So, people have, for many years, talked about this Mott transition endpoint and the similarities with the liquid-gas transition. In particular, these data from 2003 have looked at the conductivity as a function of temperature and pressure and have characterized this the critical behavior close to this second-order endpoint. And then it could be, they could argue that this critical behavior is consistent with an Ising universality class, just like the liquid-gas phase transition. Actually, they've seen mean field critical exponents in a very wide region across the transition, and very close to the transition, they can see these the unconventional, the 3D Ising exponents. Yes?
Sorry, I'm a bit confused about this. Isn't any critical endpoint in any system whatsoever always Ising given certain class?
Well, I'm talking about this particular one here. I mean, no.
But what's the surprise? That's, I don't know, as an outsider, I wonder what the surprise is. Right. Critical endpoint is always Ising given certain class. No, that's that.
No. If you couple it to if you have a volume conserving transition in a system with a finite share modulus, the transition is actually officially supposed to be mean field. David Nelson, 70s. Because of share forces. So they're long-range forces.
If they're long-range forces.
Because it's the long-range elastic forces, they should actually all be mean field.
Yeah. So the theoretical story, the last time, the coupling to phonons ignored.
Since the coupling is ignored, there should be Ising.
It should be Ising.
Yeah, in the theory, but in experiment, there should be.
I'm not claiming this is surprising. I'm just setting the stage for what I'm going to talk about later. I mean, if you agree it's 3D universality class, I think it's fine. I mean, okay? And so this is consistent with the existence of a scalar order parameter, just like in the liquid gas case. And people have looked at the coupling of the scalar order parameter with the conductivity and found a reasonably good agreement with this picture. So now, as we also heard during this week, some of these systems have strong inhomogeneities. And for instance, the case of VO2, we have seen this picture before, I think many times during this week. If you look very closely around this phase transition, this metal insulator transition here, you have these domains where the system has metallic behavior and domains where the system have insulator behavior. So you have this inhomogeneous profile. We've seen this also in Schuller's talk. And so it's here. So you have this picture that in this case, you have coexistence regions of metallic behavior with regions of insulating behavior. So within this picture of an Ising transition, if you look at this Landau functional description, we know that at above the endpoint, you have this functional with only one minimum, and you lower the temperature across the endpoint, and then you develop these two minima which correspond to insulating and metallic behavior. And of course, if you have an inhomogeneous situation and you go from an insulator on one side and a metal on the other side, you're effectively going over this barrier from the insulator to the metallic minimum. So the domain wall between the metal and the insulator is actually has to go over this barrier and has to pass through this maximum here, which is the center of the domain wall, and this corresponds to an unstable solution to the Landau functional description. So the question is, can we look at the, should we look not only at the minima of the insulating and metallic minima, but also at what happens in this transition region from the insulator to the metal, and look at what the characteristics of this solution is. So we decided to have a look at this, at the solution, at this transition, at this unstable solution, at this maximum between the metal and the insulator. Of course, in the domain wall, you interpolate continuously from one to the other, but let's look at the center of the domain wall where you have this strange situation, this unstable solution. So in order to do that, you have to be able to describe an inhomogeneous system, and what we did was to use the so-called the dynamical mean theory that we heard about many times here, but now generalized to this inhomogeneous situation where you can retain the assumption of a local self-energy of your electrons, but now because of the inhomogeneities, you allow the self-energy to vary from side to side. So this is very much in the same spirit of dynamical mean field theory, except that now you have one self-energy for every site, so you have a spatially fluctuating self-energy. Of course, you have to do this self-consistently. Every site sees all the other sites, and you have to have a self-consistent solution to this whole problem. Now, I call your attention to the fact that at zero interactions, if you take into account the full inhomogeneities, at least in a numerical way, this is an exact treatment. It only becomes inexact when you assume this local self-energy in the presence of interactions. So you can do that, and you can treat the problem, can look at the problem within this picture, and you can, for instance, look at the imaginary part of the self-energy as a landscape picture of a 2D lattice. This is a 20 by 20 2D lattice. As you cross the transition from here, so here is a metallic solution, you're going into the insulating solution. As you are close to the transition because of the inhomogeneities, you see very clearly these puddles of metals and puddles of insulating forming as you crank up U. So you see that you have very large, so if this is the Mott insulator, you have very large domain walls surrounding these puddles. So the question of the behavior within the domain wall becomes a very important one. Okay? So you can also do this, a simple 1D calculation where you go from insulator to metal, and you also see this domain wall picture. And so let's now look at the solution at this midpoint of this domain wall.
Just a question, your calculation is in 2 dimensions.
Which one? The picture here is in 2D, yeah.
But the calculation is well, right?
Okay, so this is a 2D fully self-consistent calculation. What we're going to do now is different, okay? We're going to look at the impurity problem, okay? And, okay, so we're going to look at the, we're going to look at the homogeneous system, okay, which has the Mott transition, the conventional Mott transition. But we're going to look at the unstable solution at the top of the mountain and see what happens as you decrease U inside the coexistence region, okay? So what I showed before here, this is the fully self-consistent stat DMFT solution. This is a Hubbard model with diagonal disorder, the same Hamiltonian I showed before, okay?
And it's solved by exact diagonalization?
No, this is Monte Carlo. Hirsch-Phi Monte Carlo, okay? So now what we're going to do is to take the uniform Hubbard model, but we're putting ourselves at the top of the unstable solution and see what that gives you. So there's two ways you can look at this. So this is the transition. This is the endpoint, the second order endpoint. This is the transition line. So you can go down in temperature along this first order line precisely where the metal and the insulator have the same free energy. So when you do that and you lower the temperature along this line, what you realize is that the unstable solution, which is given here by these green lines, so the metal is the black line. You have this nice quasi-particle peak. The insulator has a temperature-forming gap. But the unstable solution still has a very clear quasi-particle peak. As you lower even further the temperature, the unstable solution, the green line, still has this very characteristic quasi-particle peak. So you can now focus on this behavior, and you can extract the self-energy behavior of the unstable solution as you decrease the temperature, and you realize that because this has this quasi-particle behavior, you can parameterize it with a Fermi-liquid type of description with the Z quasi-particle residue Z and the gamma and a broadening gamma, and you can follow the behavior of these two quantities as you decrease the temperature. This is, again, the green line is the unstable solution, and you see that even at the lowest temperatures, Z is a well-defined quantity, although it depends on the temperature. So this is reminiscent of this resilient quasi-particles that people have talked about in the last few years, where you can even, in a finite region of temperature above the Fermi-liquid coherence, you can still talk about a quasi-particle picture with a well-defined quasi-particle residue. But I call your attention here to the fact that although you can still talk about quasi-particles, the gamma, the imaginary part of the self-energy is very large. So it becomes small at low temperatures, but as you crank up the temperature and you go towards the critical endpoint, this becomes a very large gamma, very large scattering rate. So if you take now these two quantities, and you can then use this in a calculation in the MFT spirit of the resistivity of the system, you find that although there's a lot of scattering, it's not too far from the metallic solution. So this is like a bad metal behavior, an incoherent metal behavior, but with resilient quasi-particles. I'm sorry. So now again, instead of going down in temperature along the first order line, you can also go down along a fixed U line. So instead of doing like this, I'm doing like that. And do the same thing, look at the unstable solution, and you still see quasi-particle peaks. Okay, again, the unstable solution is the green line. This very, very clear quasi-particle peak here. And here, though very tiny, you can still see and characterize the quasi-particle peak at the lowest temperatures. Once again, you can do the same type of analysis. You can find the Z, you can find the gamma. And once again, Z goes down to very low values with decreasing temperature. And gamma, now very surprisingly, has very large values. So this, although you can talk about resilient quasi-particles, there's a lot of scattering. This is way above the Mott limit. And as a function, so if you now look at the resistivity as a function of temperature, this doesn't look at all like a metal. It's actually going down. Okay, so now, so the picture that I have to show it to you, the take-home message here is that we have this very strange behavior at the center of the domain wall, and if the system has these very large domain walls between the metallic and insulating puddles, this may be very relevant if you want to understand the transport property of this inhomogeneous system. Of course, this is just the beginning of the story. We'd like to have a full calculation with full inhomogeneities in the system with full domain walls to see what happens. But this is already a hint that the strange behavior at the center of the domain wall will play an important role when you calculate for the full system. Okay. Excuse me.
The domain wall is a width, and then now assume a homogeneous state, and when the width gets smaller, there's a critical distance, then the picture should qualitatively change. But I guess you will later make clear that there's it's sort of natural to assume that the width is sort of large enough that this behavior survives.
That's right. Yeah. That's right. That's the point. Okay. So now I'm going to move along and talk about disorder effects in superconductors. So I start by reminding people of a very well-known fact that, for instance, high-TC superconductors are known to be very insensitive to disorder. So I quote here from the so-called consensus document that we heard about yesterday on high-TC. There is this quote from that paper that some fundamental aspects of high-TC superconductivity are still qualitatively not very well understood, like the influence of quench disorder, and the fact that the D-wave superconductivity in these systems seems to be fairly insensitive to disorder is a puzzle. As you probably know, D-wave superconductors, according to conventional theory, the superconductivity should be destroyed very easily with non-magnetic disorder. But this is not what is seen in these systems. These are very robust superconductors. So for instance, if you look at these pictures of the local density of states in a sample, as you look at different points in the sample, although there's a lot of spatial fluctuations at large energies, the low energy region is fairly insensitive to disorder. Okay, so this has been looked at in the context of the TJ model using the so-called projected Gutzwiller wave function, or equivalently RVB slave bosons wave functions by these people, and they have found very remarkable similarities with the experiment. So this is actually a numerical calculation within this slave boson theory, and you can see that the low energy behavior is very insensitive to disorder, although at higher energy you still see strong fluctuations. So just very quickly, these kinds of calculations are done using this slave boson trick. You have these C creation operators which are constrained to have no double occupancy, so you can substitute this by an auxiliary boson, an auxiliary fermion, and at the mean field level, this boson is condensed, and you have these, which I call R fields, and you have sort of a separation between degrees of freedom describing the charge and degrees of freedom describing the spins, so-called holons and spinons. You have to enforce the constraint that the number of B's and F particles is 1 on every side, and you do this with a Lagrange multiplier, which I call lambda. And you also decouple the J term into a singlet bonds and superconducting bonds across the bonds between two sites, and then you have a mean field theory for these values here, for these parameters here.
Can one rationalize this numerics if one looks at the distribution function for chi's and deltas?
Yeah, that's precisely what I'm going to talk about. So this is essentially a numerical calculation where this was observed, and I remind you that here we have no gauge fluctuations. This is just at the saddle point. So the question was precisely that. Can we gain some analytical insight into this numerical result? So this is what we tried to do. And so the way we did it was by looking at an expansion in disorder. So we basically linearized the theory around the clean limit, taking the first non-trivial term in the disorder. So essentially, all of these mean field parameters you can expand in this disorder potential, and you can find, of course, to linear order, all of these quantities here are calculated within the clean limit. So you can easily calculate this in the clean limit. They are translationally invariant quantities, and you can Okay, it's a lot of calculations, but you can do that. So now, when you do that, you realize a number of facts. So the first thing that we realize is, first of all, that the fluctuations of these chi fields are completely negligible, right? So if you put them in or not, you get the same result. So you can't just throw away these fluctuations. And then you're left with the other fields, okay? So the R, the lambda, and the delta fields. And you can integrate out the lambda fluctuations and look at what happens with the other fields. So when you do that, you can write the gap fluctuations as a function of the R fluctuations. So this is very easy to do. This is not surprising because everything here is linear. So of course, if everything is linear in epsilon, they're proportional to each other. And of course, because of this constraint that I talked about, the number of bosons times the number of fermions has to equal 1, there's a direct relationship between these fluctuations and the charge fluctuations. Okay, so that's what you get. And now, I think the important thing we found out here is that this quantity, which is sort of a charge pair correlation function, is actually a very featureless quantity of order 1. So if this thing here is suppressed, this will be suppressed by the same amount. And since this is a Mott system, and essentially what this R field is doing is describing Mottness. It's describing the small charge fluctuations that happen because of strong correlations. These charge fluctuations are suppressed, and consequently, the gap fluctuations are suppressed together with it. So this is what we call Mottness-induced healing. So the upshot here is that we could ascribe the small fluctuations of the gap to the small charge fluctuations in a strongly correlated system. So just to demonstrate this, if we look at sort of the response of the gap to the disorder, you get basically a hump. Okay, so there's a non-local part that I didn't include here, but this is very tiny. This is 2 orders of magnitude smaller than this what I call the local response. And so you get this hump close to 0. If you do the same thing for the charge, you also get this hump, and suggesting that there's a strong connection between these 2 quantities. Now, if you look directly at the gap fluctuations, for instance, at doping 0.2, and you look at the charge fluctuations at the same doping, you see that they are very much suppressed. If you now by hand turn off the strong correlations, you have much larger gap fluctuations and correspondingly much larger charge fluctuations. So the take-home message here is that the suppression of gap fluctuations is strongly linked to suppression of charge fluctuations. Okay.
Question.
Please.
I see it perfect, right? You're assuming you cite disorder. Right?
Yes.
And it's all about intensities. When you assume bond disorder, this is still true. I mean,
yeah, that's a good question. I'm talking about disorder, non-magnetic disorder. I'm not damaging anyhow the spin lattice, right?
I can split it with it, right? So the bond disorder, you fluctuate with energy on bonds. As far as I recall it, there's still, in the case of the Anderson sealer, the Bedford universal conductivity. Now, the energy is not directly talking to the charge density. The charge density is flattened, as you explained, and I know why, I understand that. But perhaps you could still have a lot more surviving of the bond energy fluctuation.
Yeah, I mean, if the Baire disorder couples to the bond variables, then I can't really answer that question. And people have looked at this, but we didn't do this.
I think I can say something here. You know, because this is self-consistent, so you put something for dimension here. The question is, does it spread to long distances? So it's basically a boundary condition. And what is the local nature of this perturbation, as long as it's local, doesn't affect long distances. And what we found that, you know, in weakly correlated system, it spreads out because of middle oscillations, and then long distance propagation is basically strongly suppressed. So I don't think that this result strongly depends on the
Well, but I mean, I should say there are studies of other types of disorder that show, for instance, local magnetic moments formation within the system. We're not looking at that.
That's a different story, right?
Yeah, yeah.
This is a question, perhaps you can easily check it, right? By doing what they for one disorder, see that yes, is it right?
Yeah, my suspicion is that it's not very important, but okay. Okay. Yeah. No.
But here, when you expand another mean fields, we still not fluctuations?
No. We do not consider gauge fluctuations. We are just considering spatial fluctuations due to disorder. Okay? No, I'm not. Well, people can hardly do it without disorder. I mean, we didn't do it. I mean, this is a very well-defined calculation at the mean field level. Okay, I think the honest answer is the following. Of course, I can't not know what you're asking, but all of these gauge fluctuations, they start from a mean field state, right? You have to have a well-defined mean field state around which you allow the gauge fluctuations to exist. Now, if the mean field state is strongly modified by disorder, you have to first determine that before you allow for the gauge fluctuation. Okay, what I'm saying here is that disorder has a very strong and easily understandable effect on the mean field solution. That's the point that I'm trying to make here.
I mean, I can read it because you said about physics, right? Because of the strong interactions, your electric system gets way more incompressible.
Absolutely. That's it. That's right. That's right. Well, you see, I mean, these data, were known, but it was kind of unclear what was going on. Okay, I'm not saying that this is very fancy physics. I'm saying that it's very easy to understand what's going on here. Okay.
Well, the fact that you have delta fluctuations is consistent with the fact that you keep having particle symmetry. But you were rather quick in saying that chi doesn't fluctuate or is small. If it were to fluctuate, I would raise the particle whole symmetry, right?
Yeah, but we did the calculation with and without the chi, and we saw no difference.
Why is chi not fluctuating?
No, okay, why the self-consistency doesn't let it? I'm not sure I have a simple answer to that.
It comes to second order. The leading order is not, this is for weak disorder. So to leading order, this is sub-leading.
No, but it's not true. It exists to leading order, but it's just small. It's just parametrically small. Okay, but this term is not zero. It's finite. It's just small.
You evaluate this thing, right? You have an analytic expression for Mij.
Absolutely.
So, and if I look at it, can
Yeah.
I see why it's small?
Probably. I mean, I didn't do that.
Okay.
This is my own disorder question.
Yes. I'm just saying that the result is that it's small. That I know for sure. It's probably easier to look at it and give you an answer for that, but we didn't do that. Okay. Okay. So now, for the last part of the talk, let me talk a little bit about the superconducting state. Actually, I was talking about the superconducting state when I talk about the TC suppression by disorder. So within this mean field theory that I just described, there is this well-known phase diagram where you have these various phases. Basically, this line here determines where this B field condenses. This line here determines where this delta field condenses. And in particular, in the overdoped region, within this theory, TC, superconducting TC, coincides with the appearance of the delta condensation. Okay, so TC in the sense it's very much like BCS theory. It comes from the appearance of a BCS order parameter along this line here. Now, within the same theory, of course, at this particular line, all the other fields are very well condensed because they condense at higher temperature. And so you can look at this particular line and ask whether you can say something about the effect of disorder on TC by assuming that all these other fields are well condensed and you can take them at their zero temperature value. So if you do that, in essence, the theory for TC is just like BCS theory for these spin-ons, for the F electrons, and we can try to extend the Abrikosov-Gorkov theory of TC suppression by non-magnetic impurities within this, this D-wave superconductor. That's what we did. And of course, the answer is actually very simple. So we did this once again to linear order in the disorder, and Abrikosov-Gorkov theory tells us that the important parameter you have to determine to find the TC suppression is this pair breaking scattering rate, 1 over tau PB. And what you have to do is calculate this. It's given by an expression like this. So this is the effect, the scattering of the F electrons of an impurity, except that because of these other strongly correlated fields here, these fields that describe strong correlations, the disturbance is actually dressed. So if you have an impurity here, there's actually a whole disturbance around a finite region around this impurity, and that's what actually comes in and scatters your F electrons. So in other words, what you have to put in here is not the bare impurity, but the dressed impurity, dressed by the spatial fluctuations of these other fields that we calculated before. Okay. So we need to calculate this here. I just call attention to the fact that this cosine factor here just comes from the angular dependence of the gap function. So what we have to do is to put in here the dressed potential scatter of an impurity dressed by these field fluctuations around it. So when you do that, you realize, for instance, that this renormalized T matrix, it's first of all renormalized by this X factor, which is basically R squared. So this is strong correlation effect. Okay, so the pairing electrons are F electrons. The F electrons are suppressed by X. So the first effect is a suppression by an X squared term, but also the theta dependence is changed. Okay, so if you put a delta function impurity, it has no K dependence in K space, so this is very localized impurity, but of course, as I showed you before, the disturbance is not confined to one site only. It becomes a sort of a soft scattering potential, and that soft scattering potential is actually plotted here for different dopings. So for 0.5, 0.15 doping, you clearly see if you divide it by the bare impurity potential, there is a very large angular dependence of the T matrix, and there's a very strong enhancement in the forward direction. So this is basically a softening of the local potential by these charge disturbances around the impurity. Okay, you can do the same thing just to mention here to the normal electrons. If you want to find the scattering rate in the normal state, you can do the same procedure. It's also down by an X factor, but it's different from here. It's only one X factor. So the normal state scattering rate is suppressed by X. And now if you plot these two quantities as a function of X, you have this, there is a mild suppression of the transport scattering rate, but a much stronger suppression of the pair breaking rate. And so this is consistent with a small effect, a small effect on TC by impurities, basically because these impurities are softened by the strong correlations, as I showed you. So in the end, let me end up with my conclusions. I talked about basically two themes. This inhomogeneous Mott state that people have talked about suggests that it would be important to look not only at the metallic solution and the insulating solution, but also at the solution within the domain wall, which is, as I showed, very, very anomalous. And as I said also, this is sort of an incoherent or bad metal or a bad insulator at the domain wall center. And in the case of the strongly correlated superconductor, I showed that the effect of non-magnetic impurities is strongly healed by Mottness. So both the gap fluctuations are healed, but also the scattering by impurities is strongly softened, and this might be an explanation for the robustness of TC that's seen in these systems. Okay, thank you.